2.9 one-to-one functions and their inverses. A function within domain A is called a one-to-one function if no two elements of A have the same images. That is, f of x1 does not equal f of x2 whenever x1 does not equal x2. If f of x1 does equal f of x2, that means x1 and x2 are the same value. You have the same x value twice. So we now have the horizontal line test. You had the vertical line test, which tested if it was a function. Now we know it's a function, and we're testing if it's one-to-one. So a function is one-to-one if and only if no horizontal line intersects its graph more than once. So we're going to make a curve. And we're going to try the vertical or the horizontal line test. So I have this horizontal line, and we're testing if it hits anywhere more than once. So starting at the top, it's only hitting the line at one spot. So this one is one-to-one. Here we have a curve, and we can see right away it's hitting the horizontal line in 3 spots. So this is not one-to-one. Okay, we're going to decide if a function is one-to-one. We're going to start with f of x equals x cubed. And we've seen this graph before. And if we try the horizontal line test, we see that it will pass. So yes, f of x cubed is one-to-one. If we try f of x equals x squared, we know that's going to be in the shape of a parabola. And we can tell right away that this is not one-to-one. All quadratics are not one-to-one, so no quadratics are one-to-one. So now we're going to show that a function is one-to-one. Suppose there are numbers x1 and x2 such that f of x1 equals f of x2. So we're assuming, we're being told that f of x1 equals f of x2. So if that's true, then we get f 5 times x1 plus, minus 2 equals 5 times x2 minus 2. So solve for x, add 2 to both sides. So we get 5x1 equals 5x2 divided by 5. we get x1 to equal x2, which we know is not true. Therefore, f is 1 to 1. I'm sorry, I meant to say, therefore they are the same value, so therefore it is 1 to 1. The inverse of a function. Let f be a 1 to 1 function. And 1 to 1 functions are important because they are precisely the functions that possess inverse functions according to the following definition. So, an inverse function, let f be a 1 to 1 function with domain A and range B. Then its inverse function, f inverse, has domain B and range A. So, what we're doing is we're switching where the x and y are. So, they switch their domain and range. So we're going to find the f inverses for the specific values. If f of 1 equals 5, f of 3 equals 7, f of 8 equals negative 10, we're going to find f inverse of 5, f inverse of 7, and f inverse of negative 10. So for f of 1 equals 5, we switch their placement and we get f inverse of 5 to be 1. For f of 3 equals 7, f inverse of 7 is 3. For f of 8 equals negative 10, f of negative 10 equals 8. The property of inverse functions says let f be a 1 to 1 function, so we're assuming it's 1 to 1, with domain A and range B. The inverse function f inverse satisfies the following cancellation properties. So if you take the inverse of the function, it goes to x. If you take the function of the inverse, it goes to x. So an inverse and its function cancel each other out. F and f inverses are inverses of each other. Okay, so we're going to verify that f of x equals x cubed and g of x equals x to the 1/3 are inverses of each other. So we do this by taking composites, f of g, and then we're going to do g of f, because it needs to be both directions. So for f of g, f of x is x cubed, g of x equals x to the 1/3. We're taking this, plugging it in here. So f of g goes to x to the 1/3 to the 3rd power. And we remember rules of exponents, they will multiply. X to the 1/3 times 3 goes to x. Okay, so when we do g of f, we want the same outcome. We want x. So, which is also stated by our property. So g of x is x to the 1/3. F of x is x cubed. We're taking x cubed and plugging it in right here. So g of f takes x cubed to the 1/3, multiply the exponents. X to the 3 times 1/3 goes to x. Therefore, they are 1 to 1 inverses. So steps to finding if the inverses are 1 to 1. We write out y equals f of x. We change where x and y are, and then we solve for y if possible. If it is possible, our answer that we get out is f inverse. So, for example, we're known to find the inverse function of f of x equals 4x minus 9. So, f of x is the same thing as y. We change the x and y location and solve for y. Add 9. So 4y equals x plus 9, and divide by 4. So y equals 1/4 x plus 9 over 4. Last step, we rewrite it as f inverse of x, which is 1/4 x plus 9/4. Let's go to a little bit more complicated problem. F of x equals x to the 4th plus 5 over 3. So I'm saying y equals x to the 4th plus 5 over 3. I change my x and y. X equals y to the 4th plus 5 over 3. And I solve for y. So first thing I do is I multiply by 3 on both sides. So I get 3x equals y to the 4th plus 5. Subtract 5. 3x minus 5 equals y to the 4th. And it's to the 4th, so I had to 4th root it to get it all up. So I get the 4th root of 3x minus 5 equals y. Last step, set it equal to f inverse of x. The principle of interchanging x and y to find the inverse function also gives us a method for obtaining the graph of f inverse, given the graph of f. All you do is you reflect it over the line y equals x. So in the coordinate plane, I have the line y equals x, and then I might have the following curve, f of x. Its inverse is reflected, and we've worked on reflections before, over the line y equals x. So this is f inverse of x. So we're going to actually graph an inverse function. We're going to find the inverse function graphically. So part A says sketch the graph of f of x equals root x minus 3. Okay, root x is the base. We're subtracting 3. That means it moves it to the right 3 units. So we can graph this as such. Okay, we now need the line y equals x. So we now have the line y equals x. We see that y equals x goes through the origin. Now, we're 3 to the right, so when we reflect it, it's going to be 3 up. And then we're at 4, 1, we're going to be at 1, 4. We're at 7, 2, we're going to be at two sections. So we now have the graph of f inverse of x using f of x and reflecting it over the line y equals x.